In this video, I'm going to talk about finding limits at boundary points on a region in space. When I have interior boundary points, it means that if I have a region in two-dimensional space, then a point that lies entirely within this region, let's call the point P and the region R. This means that if point P lies entirely within the region R, that I can find a disk centered at P that will contain only points that also exist in R. So that some arbitrary region R with a point P located somewhere in the interior can be surrounded by a disk that contains only points that are also contained in R. But if I have a point Q that lies on the boundary or the edge of this region R, then the disk that I create will contain at least one point that lies in R, but also at least one point that doesn't lie in R. This is in two-dimensional space. Let's talk about interior boundary points in R3. This time, my region is going to be a region in three-dimensional space, and for simplicity's sake, I'll represent it as a sphere. If an interior point P of this region lies entirely within R, then it is possible for me to find a ball centered at the point P that only contains points that are in the three-dimensional region of R, so that I have a point, I can surround it by a ball, and every point located in this ball will also be a point in my three-dimensional region R. If I find a point Q that lies on the edge of my region, then a ball centered at this point Q will contain at least one point that is in R and at least one point that is not in R. Now I want to talk about open and closed sets very quickly. A region is open if it consists entirely of interior points. In other words, it doesn't contain any of the points on its boundary. And a region is closed if it contains all points plus the points on the boundary. So that an open region might look like the set of all xy such that x squared plus y squared is less than 1. This in xy space graphs as a circle centered at the origin, but the boundary of the circle is not included because it's a strict inequality, so I have to graph it with a dotted line. A closed set might look like the set of all xy such that the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1. This is a square, and it consists of all the points inside the square plus the points on the boundary of the square. So let's work some examples. We want to evaluate the following limits. The first one is the limit as xy goes to -1, 1 of the rational function given by the quantity 2x squared minus xy minus 3y squared all over the quantity x plus y. The second limit is the limit as xy approaches 4, 5 of the rational function given by the quantity the square root of x plus y minus the value 3, all divided by the quantity x plus y minus 9. In both cases, direct substitution gives us a limit of indeterminate form. For the first example, where I want to find the limit as xy approaches -1, 1 of the rational expression given by the quantity 2x squared minus xy minus 3y squared all divided by x plus y, I'm going to factor the numerator in my expression. It gives me the limit as xy approaches -1, 1 of the quantity 2x minus 3y times the quantity x plus y, all divided by x plus y. The x plus y terms cancel in top and bottom, simplifying my limit to the limit as xy approaches -1, 1 of the quantity 2x minus 3y. I can find this limit using the difference rule, or I can use direct substitution. With direct substitution, I get 2 times -1 minus 3 times 1, which is equal to -5. In part B of this example, I want to find the limit as xy approaches 4, 5 of the rational function given by the quantity the square root of x plus y minus 3, all divided by the quantity x plus y minus 9. In this case, I'm going to multiply the top and bottom by the conjugate of the numerator. I get the limit as xy approaches 4, 5 of the quantity square root of x plus y minus 3 over the quantity x plus y minus 9 times the ratio the square root of x plus y plus 3 over the square root of x plus y plus 3. I'm going to do that multiplication. I get the limit as xy approaches 4, 5 of the quantity x plus y minus 9 all divided by x plus y minus 9 times the quantity the square root of x plus y plus 3. Notice that the terms x plus y minus 9 cancel in top and bottom, again simplifying my limit. I get the limit as xy approaches 4, 5 of 1 over the quantity the square root of x plus y plus 3. Using direct substitution, my limit becomes 1 over the square root of 9 plus 3, which reduces to 1/6. So now you get to try it. Pause the video and evaluate the limit as xy approaches 8, 8 of the rational expression x to the 1/3 minus y to the 1/3 divided by x to the 2/3 minus y to the 2/3. When you're ready, restart the video to check your understanding. To evaluate this one, I'm going to factor my denominator. I'm going to rewrite my limit as the limit as xy approaches 8, 8 of x to the 1/3 minus y to the 1/3 divided by the quantity x to the 1/3 minus y to the 1/3 times the quantity x to the 1/3 plus y to the 1/3. The terms x to the 1/3 minus y to the 1/3 cancel in top and bottom, so that I'm left with a simplified limit, the limit as xy approaches 8, 8 of 1 over x to the 1/3 plus y to the 1/3. Using direct substitution, I get 1 over 8 to the 1/3 plus 8 to the 1/3, which reduces to 1/4. This is how we can take limits of functions that exist at boundary points by looking for opportunities to simplify the limit we're working from in the first place. Be sure and let me know if you have any questions about taking limits of functions of two variables at points that exist on the boundaries.